we're going to look at now ratio tables, which is basically just a table with equivalent ratios. And we're going to look a little bit about reasoning on different ways to look at equivalent ratios. So we're going to have some of the formats to show how they are all related. The last part about solving problems using graphs we're going to do on our next class section. Tonight's homework, really simple. It's just the next 2 sections in Mathia. As a reminder, your Mathia grades are all going in on Friday, so you guys should be at section 5 out of 20 in module 2, or a total of 34 of the 129. Okay? So everybody should be on page 211 right now. Page 211 in your books. That's just a review of your learning goals. Down here, we have a problem. We've got 1 cup of milk to make a batch of 8 pancakes. We got 3 questions to go with it. So we'll give you guys 3 minutes, try to work these out. I'll give you a hint. If you'll set the rates up, it actually makes this really simple. Go ahead and go. Guys, anytime you're doing these type of ratio problems, you have to start with your base ratio. You need to write it out. It's not difficult. It's right here. It's 1 cup of milk to 8 pancakes. That's going to be your start for every single problem. If you'll set these up, the ratio problems become extremely easy. Because literally all I got to do is copy down my units.
They're not on your paper. You need to be getting this.
On the second one, put in the number they've given me. In this case, I went to 16 pancakes. So I put a 16 here. Then you have 2 options. The way I like to do it is what we call the magic box. I draw a box and I just say, how do I go from 8 to 16? What do I do? Times 2. That goes in the magic box. So now I know I go 1 times 2 and I get 2 cups of milk. That is the work that we expect to see on these problems. If all you did was write 2 cups of milk, and this is a quiz, are you getting full credit? No, you're not, because you haven't shown any work. Same thing. My initial ratio is going to be the same for every one of these problems. So I have 1 cup of milk, 8 pancakes, equals cups of milk to pancakes. The only thing that's changed now, how many cups of milk? 4 pancakes. So I put a 4 for the pancake. My magic box, how do I go from 8 to 4? Divided by 2. That goes in the box. So 1 divided by 2 is either 1/2 or 5/10, however you want to write it. But it is a 1/2 cup of milk. Then number 3, our start is the same. 1 cup of milk, 8 pancakes, equals cups of milk, pancakes. Then I go to my problem, how many pancakes with 4 cups of milk. So I now have a 4 up here. How do I go from 1 to 4? Times 4. Then I do 8 times 4 and I get 32. We're not asking for that much work, guys. I know a lot of you were able to do this in your head. That's great. The problem is going to come next year when you're doing ratios again, and they start throwing much harder numbers because you do positives, negatives, lots of decimals, lots of fractions. You're not going to understand how this is set up and how they relate, and you're going to be completely lost. Please, we're in the process so that as the numbers change and get harder, you're still able to do it. Okay? Any questions on any of these 3? Yes, ma'am.
Do you want your side copy of what you do on the board?
They should always copy what we did on the board.
Just thought I'd ask.
Guys, if you didn't do this on your paper, you should have it written now. We worked it all out for you to have examples so you understand how to do this. Okay? We can't take forever because we've got a lot to do today, but if you miss this, Make sure you look at the video tonight to get this copied down or copied from one of your neighbors. Okay, on your density. One thing that we look at for how population works is what we call population density. It is a special ratio that compares people to square miles. Basically, here's a chart that gives us the approximate population density for 4 U.S. states in 2019. We have a couple questions for you. Which state has the greatest population density? Which state has the least population density? Explain what it means in your own words. So we've got a key down here to show you what it means. So every figure is 200 people. Every box is equivalent to 1 square mile. So if I have a half of a figure, how many people would that be? 100. If I have someone that's missing 1/4 of their body, yeah, 150, because that's 3/4. Does that make sense? So I'll give you a hint. I'll give you 2 hints on this actually. Number 1, the easiest way to solve this is actually put the numbers to the figures so that you've got numbers to work with. Secondly, if I'm looking at highest population density, is that going to be the biggest number or the smallest number? Highest number per square mile. Okay? So those 2 hints should help you understand how to do this. You got 4 different things you're doing, so we'll give you guys about 5 minutes to work through all of this, and then you can answer. We're not going to actually worry about number 2 for today, but turn all of these into written ratios, then do a comparison. Okay, guys, let me give you an example. So here's an example based on this first one, right? How many figures do I have? 1. How many people is that? 200. So I would start my ratio by saying that's 200 people. How many boxes do I have? 5. To 5 square miles. Does that make sense?
Yes.
So once I've turned them into numbers as a ratio, that gives me something to start basing my comparison on. So do that with all 4 of them. Then you can start to figure out what do I need to do to make a comparison, okay? Okay, so we already did the first one for you, so let's look at the other ones. So our second one, we got 2 whole people and a half of another one, so that makes that 500 people.
500.
And 2 square miles. This next one, 1, 2, 3, 4, 5, 6 times 2 gives us 1,200 people. And that one is just in 1 square mile. And our last one, this one's a little more difficult because he's missing a leg, so that's like 3/4. So 2 fulls is 4. 3/4 would be another 150. That gives us 550 people. And we have 6 boxes, so 6 square miles. Now, if I'm going to do a comparison, what is the most important thing that I need to do? Yeah? Common denominators. In other words, I need to have all of these as the same thing. So the easiest thing to do is take them all to 1. So whatever the number is, I'm going to divide both sides by that number to get it down to 1. So in other words, 5 square miles to get to 1, I'm going to divide by 5. So I divide by 5, I do that to both sides. That's going to give me 40 people per 1 square mile. If it's a 2, I'm going to divide by 2. So that's going to give me 250 people to 1 square mile. This one's already at 1, so I don't have to do anything to it. Then our last one is a 6, so I'm going to divide by 6. So that number doesn't work out quite as evenly, but I just do 550 divided by 6. That's going to go 9 times 54, so you give me 10, so that's going to go 1. So it's going to be somewhere around 91 people per square mile. Once I have a common denominator, now I can actually compare my numbers, right? Does that make sense to everybody?
Yes.
So if I'm looking at them, which one had the highest number of people per square mile? New Jersey. Okay? So the first answer for number one, New Jersey, has the highest density. Which one had the lowest then? Ended up being Oregon at 40. Because 91, 40, 91, 250, 1,200. So Oregon has the lowest density. Did we do everything we were supposed to on this?
Explain your reason, or what this means.
Okay, so your own words. How did we discuss this? How would you say this in your own words to talk about population density?
Most people per square mile.
Okay,
But make sure to also simplify.
that's really the biggest thing I was hoping someone would say. We need to simplify to get to the same comparison. Okay?
Through all the lost and found over here. Got those. And the ones that are over there. Yeah, there's lots around there.
Questions on those ones? Doesn't make sense. We understand now the importance of getting to that common denominator and compare. Okay? So we're not going to worry about number 2 today. We don't have that data readily available. Let's go ahead and go to page 213. 213. So this one, we're going to have a whole bunch coming up, but we're going to talk about this a little bit first. So your weight on Earth is a measure of the amount of gravitational attraction exerted on you by the Earth. The moon has a weird gravitational pull. So if I go to the moon, does my body change? No, it doesn't. My body is still the same.
If you don't have a spacesuit.
Well, that's going to be different, but my body itself will not change. What it changes is the gravitational pull. So my weight would change. My body is made of mass. It's a bunch of cells that are put together, and it's not going to change regardless of where I am. What changes is my weight based on how much gravity is pulling against that mass. So when we look at it, the ratio of the weight on Earth to the weight on the moon is approximately 60 pounds to 10 pounds. Okay? So we can use that ratio. We can now use ratio tables to show how two quantities are related. So make sure you mark that one. We haven't really talked about ratio tables yet. Actually, we should probably highlight that. So get out your highlighters, your marking pens. So we have ratio tables that show two quantities are related. It's basically just another way for us to organize our information. I didn't do highlight that text. So that's all. Okay. Here's a table that can show us 3 equivalent ratios for the weight on Earth to the weight on the moon. We start with the ratio they gave us of 60 to 10. One way we can do is we always say we multiply or divide, right? Go from one to another. So if I divide both those numbers by 2, 60 divided by 2 is going to give me 30. 10 divided by 2 is going to give me 5. Is everybody okay with that? So we can say that 30 over 5 is equivalent to 60 over 10. Now, one really cool thing, if I have a ratio table, it gives me an additional option. I can also add pieces of the ratio table together to get a new entry. So if I take 60 plus 30, I would get 90. If I get 10 plus 5, I would get 15. So that would be an additional equivalent ratio. Is everybody okay with that so far? Okay. Now, let's verify that the three ratios are equivalent. Explain your reasoning. So this gets back down to our definition of equivalent ratios. Who remembers the definition of equivalent ratios? How do we know the two ratios are equivalent? Anybody? It's in your modules, but it's a ways back now when we first started talking about equivalent ratios.
It's like specified ratios.
Okay, we know they are equivalent if they simplify to the same number. So one of the easiest ways to check if ratios are equivalent is simplify them as much as you can and see if you get the same number. So, for example, if I have 60 and 10, what can I divide both those by? 2 and 5, which means I can divide them by 10, which would give me 6 over 1, right? What about 30 over 5? What can I divide both those by? Divide those by 5, which gives me 6 over 1. What about 90 and 15? What can I divide both those by?
2.5.
15, which gives me 6 and 1.
2.5.
So they all simplify to the same number.
2.5.
Does that make sense? I don't know how you get 2.5 from 6 over 1. Austin, your math is a little questionable on that.
No, but you can divide 90 and 15 by 2.5.
So, can I show a different strategy to determine that the ratio of 90 pounds on Earth, 15 on the moon? So if I have my base ratio of 6 to 1, I can do a tape diagram. So this would be E and M. E is the Earth weight in pounds, and M is moon weight in pounds. How do I go from 1 on the Earth to 15, or 1 on the moon to 15 on the moon? What would I multiply by?
15.
15 gives me a ratio constant of 15. So if I put 15 in every box, I now have 90 to 15. Is that another way to show that those are equivalent? Why are you not writing anything down? Guys, if it's on the board, you should have it on in your module. So is that the only other different strategy I could have used? Could have used a double number line. Could have just shown with the two ratios how with my magic box, my arrows, how I went from one to the other. Draw a picture. There's a lot of different strategies we've given you guys at this point. Any of them are applicable. We want you to start getting comfortable. Personally, if you haven't been able to tell, I'm really partial to these tape diagrams. I think they're really easy because it gives you a good visualization. But use whichever one you feel the most comfortable with. But you do need to start getting used to and more comfortable with more than one. Okay, let's turn the page. Go to 214. This one gets a little complex. I'm going to talk you through it first and try to make sure you understand it. What we're doing. We've got strategies being used by Howard, Carla, Mitsu, and Ralph to determine the weight of a 120-pound person on the moon.
20.
Okay? We have 3 different strategies. They've actually given you a good clue as to which ones are good, which ones are bad. You guys remember the thumbs up, thumbs down, right? So, you have Howard showed his way. You have Carla showed a little different way. You have Mitsu showed another way. And then on the next page, you've also got Ralph. So you have 4 different people, 4 different strategies. There are 3 questions based on them. So, question 3, I'm comparing Howard and Carla. In other words, look at what they did. Tell me what the differences, what the similarities are. Number 4, explain Mitsu's reasoning. Then verify that the ratio 120 to 20 is a correct equivalent ratio. So look at what she did, make sure you understand it, and then verify it. And then 5, explain why Ralph's reasoning is not correct. Make sense? So these are a little more complex. You've got a lot of different things you're looking at. We want you to work together as a table. We'll give you guys about 10 minutes to work through all of these.
All right, so compare Howard's and Carla's strategies. What did Howard and Carla do? Yes. You first.
So Carla used a number pattern and basically just skip counted by
So-
5s to the bottom and 3s to the top.
Okay, so it's not a number pattern, it's a double
Number line.
number line. And Howard did what? A ratio table, yes? So Howard used a ratio table. And what kind of reasoning did he use in his ratio table to get the other ratio? He used multiplicative reasoning. And when we are making a smaller ratio into a larger ratio, what does that mean we are doing? I need math vocabulary. Something we talked about last class. If you're going from a smaller ratio to a larger ratio, you are scaling up. And what did he scale up by? Yes, by 2. And he said Carla used a double number line. What's important about a double number line? What did she do that was important?
Made it
What's important about number lines? That each interval is equivalent, or each interval is the same. She counted by the same thing each time on the top line and the same thing on the bottom line each time, right? So she used equivalent intervals, or she used equal intervals. All right, explain Mitsu's reasoning. What is Mitsu's reasoning? What did she do?
Kind of showed how 30 and 90 equal 120 and then 5 15 equal
Kind of. Ashton, can you say it a different way? She didn't use additive reasoning. What did she do? Additive reasoning means you add the same number to the top and the bottom. She didn't add the same number to the top and the bottom. What did she do? Max? We just talked about this one. Yes, she added 2 equivalent ratios that she already knew to create a third equivalent ratio. You should be getting this on your paper if it is not there. And I guarantee you, most of you did not use all of these words. All right, and explain why Ralph's reasoning was not correct. What did he do that was not correct? He used additive reasoning instead of multiplicative reasoning. there any questions about these three? Instead of adding the same number to both numbers in the ratio, he should have multiplied by the same number to both numbers in the ratio. Make sense?
Yeah.
All right. If you don't have it on your page yet, please watch the video to get the rest of it or borrow it from your neighbor. Turn the page, please. 5. All right, so Mitsu said, I see another equivalent ratio from Carla's work. And she showed 30 pounds on Earth is the same as 5 pounds on the moon, 20 pounds on Earth to 20 pounds on the moon, and 150 pounds on Earth to 25 pounds on the moon. Is she correct? And explain your reasoning. I want you to answer that one at the table, and I also want you to do number 7 if you finish number 6 before we go over it. Go for it. You have about 5 minutes. All right, is Mitsu's reasoning correct?
Yes.
Who else agrees that it is yes, she is correct? Does anybody disagree? Okay, who can tell me what reasoning did she use, or how did she find out that 150 pounds on Earth is 25 pounds on the moon? He said you can use multiplicative reasoning and multiply the top ratio by 5 to get the bottom ratio. What other reasoning could she have used? Axel? She could have added 2 equivalent ratios because 30 plus 120 is 150 and 5 plus 20 is 25 to create a third equivalent ratio. Yes? So yes, she is correct. And we're going to do the adding part because that's what she did on the previous page. So we're just going to continue her pattern. She is correct. She added 30 to 5 and 120 to 20 to get the equivalent ratio of 150 to 25. Any questions? But does the multiplicative reasoning that we said times 5 on both sides, does that work? It also works. Let's look at number 7. Show a different strategy to verify the equivalent ratio of 150 pounds on Earth to 25 pounds on the moon. Explain your reasoning. So in the last one, we used that she added 2 equivalent ratios. So this time, can we use that multiplicative reasoning that she multiplied this times 5 and this times 5 to get another equivalent ratio? We can use our second way, yes? So we can use multiplicative reasoning to get 150 to 25. Are there any questions about this? All right, for homework, you have 2 new Matheo workspaces. You should be at 7 out of 20 when you complete them. These will go on quarter 3's grades. Have a good day, guys.